Hello everyone, my name is Marina Montserrat Atilano Camino of Nuevo León University from Mexico, and the title of this project is Photoreforming of Fermentation by Products to Produce Hydrogen and Methane by Platinum Load on Titanium Dioxide. Okay. To start us off, the global energy demand increased exponentially together with the global warming. For this reason, the world transitioned toward renewable and decarbonized energy sources. Hydrogen and methane are becoming increasingly important mediums as versatile energy carriers. Hydrogen and methane can be used directly as fuel to produce heat or to be reconverted back into electricity through a fuel cell. Different strategies have been proposed to produce hydrogen and methane employing renewable sources and environmental friendly methods. Photocatalysis has been studied as a renewable energy inputs process and as a carbon neutral process method. Specifically, photoreforming is a photocatalytic hydrogen and methane production method with simultaneous organic reforming, being more attractive than the water splitting reaction. For example, photoreforming has a less energetically demanding reaction than the oxygen evolution reaction, allowing the hydrogen evolution reaction and improving the process efficiency. Other advantage is that organic waste of biomass can be utilized and further converted into valuable organics. It is well known that the anaerobic fermentation process generates high quantities of organic byproducts as volatile fatty acids as acetic, propionic, and butyric acids, as well as some solvents like ethanol and butanol. These organic byproducts can be harnessed as sacrificial agents in the photoreforming process to produce hydrogen and methane. For this reason, the aim of this research was to produce hydrogen and methane by the photoreforming of fermentation organic byproducts of using platinum titanium dioxide as a photocatalyst. So, the experimental procedure began with a thermal synthesis where platinum was loaded on commercial titanium dioxide by chemical reduction by sodium borohydride. The obtained material was characterized by diverse techniques as XRD, BET, DLS, cytometry, SAM, EDS, XPS, and DR-UVB spectrophotometry. Finally, the photoreforming experiments were carried out using synthetic mixes similar to the previously reported fermentation by products composition. Additionally, the effect of the water matrix was evaluated, incorporating phosphate buffer into the ionized water, we show as PB, and with raw deionized water, we show as VW. All the photocatalytic tests were developed using UV LED as a source of light with a maximum wavelength emission at 365 nanometers in a batch stirred tank reactor with nitrogen atmosphere and 0.5 grams per liter of catalyst load. Hydrogen and methane concentration were measured by gas chromatography with a thermal conductivity detector during 6 hours. Okay, sorry for this. We need to zoom the image. Okay. The results are shown in figure 1. At letter B, we can find the XRD analysis that corroborates and attests as the unique crystalline phase of the selected commercial titanium dioxide. Also, seen in letter A, according to SAM characterization, the particle size of titanium dioxide was about 40 nanometers with platinum aggregates from 2 to 10 nanometers. These aggregates were homogeneously distributed on the surface on the photocatalyst, and the EDS analysis demonstrated the presence of titanium, oxygen, and platinum. Additionally, at level C, the platinum content was calculated with the XPS technique, being around 1.46 atomic percent as metallic platinum. Further, in letter D, we show the optical properties of the synthesized material, the absorption and scattering coefficient of the material, and the spectral power distribution of the emitting light are shown in order to observe the harnessed energy of light by the synthesized material. The scattering effect will be enhanced at 365 nanometers. However, the absorption coefficient values will be higher at lower wavelengths. The energy gap was estimated by Kuhlmann method, obtaining 3.2 electron volts, being similar to previously reported values. In Table 1, we can observe some physical-chemical properties as the specific surface area, similar to the reported in literature, and the hydrodynamic diameter of the particle that represents the size of the aggregates in the reaction assays, being around 211 nanometers. Then we can see the zeta potential at pH 5.3 for both matrices were negative, and this helps us to relay the possible interaction between the platinum, titanium dioxide particles, and the organic acid and alcohol molecules. Okay, now furthermore, bare titanium dioxide and platinum titanium dioxide were evaluated as semiconductors for the production of hydrogen and methane from the photoreforming of fermentation byproducts in solution under UV LED irradiation. The fermentation product consists of acetic acid at 10 millimolar, butyric acid at 4.5 millimolar, ethanol at 8.5 millimolar, and butanol at 1.7 millimolar. The photocatalytic assays were performed at pH 5.3 using the ionized water and phosphate buffer as matrix solvents. Figure 2, letter A, shows the hydrogen and methane photoreforming kinetics. The higher production of hydrogen was 2,218 micromoles per gram of catalyzed and 119 micromoles per gram of catalyzed for methane, reached using platinum load on titanium dioxide in deionized water, while bare titanium dioxide reached only 18 micromoles of hydrogen per gram of catalyzed and 44.5 micromoles of methane per gram of catalyzed. Experiments with platinum load on titanium dioxide and phosphate buffer decrease 58% of hydrogen production and 63% of methane production, whereas bare titanium dioxide only produced 8 micromoles per gram of catalyzed of hydrogen, and methane was not detected. In addition, in Figure 2, letter B and C, we can observe the reusability cycles for hydrogen and methane, respectively, wherein both energy carriers, the photocatalytic activity decreased in each cycle. This fact could be related to the platinum lixiviation or due to the photocatalyzed poisoning that caused the decrease in the efficiency on the hydrogen and methane generation. Finally, the proposed mechanism of this material is shown in Figure 2, letter D. First, once the semiconductor is activated by UV light, the separation of charge is achieved, and consequently the holes could react with the water and generate hydroxyl radicals. Also, the holes could react with the organic byproducts, producing protons, carbon dioxide, and some intermediates. Then, protons are reduced by trapped electrons on the platinum atoms, and their hydrogen is produced. In the case of methane, this can be formed by the reaction of acetic acid. And at the end, as conclusions, the role of the platinum was remarkable because of the creation of a Schottky barrier that captured the photogenerated electron, causing an evident improvement in photocatalytic activity. Also, the metallic platinum generates plasmonic effects that improve the photon absorption coefficient and increase the effective use of emitted energy to the system. The presence of inorganic anions like phosphate anions affect notoriously the photocatalytic reaction due to the competition for holes, electrons, or another radicals. Specifically, the phosphates can be adsorbed over the titanium dioxide surface at a wide pH range, and scavengers the electron to be reduced to phosphate. Finally, liquid fermentation byproducts can be used as sacrificial agents in a photocatalytic process to be converted into energy carriers, but a pretreatment is recommended to remove inorganic anions in order to improve the efficiency of the photoreforming process. You can find some reference at the bottom of the poster and the acknowledgement. If you have any question or you want to put in touch, please send an email to marina.atilano@hotmail.com. Thank you so much for this video.